Hello everybody, and this is my Breakthrough Junior Challenge video representing the Diracs equation, which discovered the positron. At the beginning of the universe, there was just one condensed ball of energy, although this ball was then our universe. However, then it exploded like... You've probably heard of E equals mc squared. Actually, who hasn't? It's basically a theory that mass is highly concentrated energy. Like this. Where all these dots here are basically energy that has been concentrated into mass. This mass came in supersymmetric pairs at the beginning of the Big Bang. Basically, two particles of a pair that have the same mass and the same properties, but opposite charges. Think of it as two twins. One good twin and one evil twin. They're still the same age, height, build, intelligence, and they've still got the same skill level, but one's evil and one's good, like the two showed here. But until the rat came along, antimatter was not even mentioned or observed in our galaxy as far as we know, which made it pretty hard and kinda impossible to observe. So we could talk about it, or we could mention it. So until Dirac's discovery, we thought more about the future in jazz music than the positron. Exactly, we didn't think about it. But however, without Dirac, we wouldn't have had awesome experiments like the Bevatron. Trust me, it's as cool as it sounds. And CERN, and the CERN anti-proton decelerators. Dirac's discovery was also not a one-field thing. It stretched into astronomy and even chemistry a little bit, creating anti-elements like anti-hydrogen, which has been newly found, which, as you've probably guessed, is a supersymmetric particle to hydrogen. Dirac's discovery was also so amazing, it won the Nobel Prize, which was the most prestigious science prize in those days, and it still is one of the most prestigious. A funny story actually, Dirac didn't actually mean to discover the positron, but only discovered it because the already formulated equation based on quantum mechanics by Schrödinger, an Austrian scientist, also coincidentally Dirac's rival, but ultimately sharer of the Nobel Prize, failed in relativistic conditions. The Schrödinger equation predicted the properties of any body or system with a non-relativistic speed, a speed that's very low compared to the speed of light. But when the particle or body or system got near the speeds of light, it just didn't work, like black shoes and white socks. I know what you're thinking. That's Greek. Well, you'll be partly right saying that. Most of the symbols are Greek. Like those weird D sort of things. And the wave functions, which look the tridents, basically. They're Greek. And so is that thing that looks like a cross between a T and an H. It's called Planck's constant. But it's not Greek. It's just Dirac's equation, in which he used to find the electron, the above, and the positron, the one below. But to get to Dirac's equation, we have to look at the other equation, which attempts the motion of the non-relativistic body or system, the Schrödinger one. It just didn't work, like I talked about earlier. I know, I'm sorry, we've got to go through another equation. But let's go. This doesn't work, as you can see. Planck's constant is very small. The mass of the electron too is very small. So for particles like the electron, if you take into account all of the wave functions and the differentials, it gives the energy of light speed at all times, because it's constant. That is just impossible. It's kind of like saying Usain Bolt is as fast as light. He is really, really, really fast, but not that fast. No living thing can reach those speeds. But now let's look at how Dirac rectified this. that were the dimensions of space-time. Time is the first one, then the X, Y, and Z. You may not have heard of these, but it's basically height, width, and it's basically width, height, and length, respectively. No, sorry, swap the X and the Z. So it's length, height, and width, respectively. The Z gives it the 3D aspect. It's like, imagine a 3D graph. He used this. These were then added to the equation, combined with 1 over light speed, and which was made to act on the wave function, and that gave the accurate motion of the electron about the nucleus of its atom. That's also English, and it basically means how the electron went around the nucleus of the atom, and using this, he managed to arrive at the equation. The top part is the equation, which found the properties of the electron, the proper properties of the electron. However, the positron was found in the second equation. The one at the bottom. Dirac realized by adding a negative wave function by replacing the positive wave function with a negative one, but changing the sign to a +1 over light speed, that gives the same output with the same properties, the same motion, the same energy, just with a positive charge, as you can tell by the positive wave function. This was quite a big prediction. A supersymmetric particle. No one had ever heard of anything like this before. Dirac had actually predicted antimatter. You can even try this out for yourself. That's if you know differential calculus. But you can try this out for yourself and see that it works. Dirac had actually predicted antimatter. This was a real prediction. Unlike most other predictions, which are explaining or advancing or developing on stuff that was already known. This was a completely different thing that no one had thought of before. And which is why it was worthy of the Nobel Prize and was one of the most significant turning points in the history of particle physics. And yes, that is long. It's been going on since 1905, since Einstein published his theory of special relativity.